Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. In the last few lectures, we discussed about the numerical methods applicable for single variable optimization problems. However, in the real world engineering problem, you will find most of the problems are of multivariable. These problems, when we try to use the numerical methods, you will find that some of these numerical methods are derived or extended version of the single variable optimization problem algorithms. So a better understanding of the single variable optimization algorithms are going to be useful to understand the multivariable optimization algorithms. In the next few lectures, we are going to discuss the algorithms for numerical methods to solve the multivariable optimization problem. Let's start with that. The various algorithms available to solve the unconstrained multivariable optimization problem numerically can be broadly divided into two categories. One is the direct search methods and the second one is the gradient based methods. So in the direct search method, you will see that these methods can be of random search methods, grid search method, univariate method or pattern search methods. So in the next few lectures, we'll be discussing about the direct search methods. And to start with the direct search method, today we will start about the random search methods. The random search method is a variation of the algorithm where we actually use the random numbers to find out an optimum solution for a given multivariable objective function. And in this case, we particularly use the random numbers to find the optimum solution. Some of the well-known random search methods are random jumping method, random walk method with direction exploitation. Let's start with the random jumping method. The random jumping method considers a search space which is represented by various random locations and the function values are evaluated at all those locations to find out where we can obtain the optimum solution for the given objective function. Now to look into the algorithm, it is very simple. Each variable can be represented by its lower and upper bound, and once we know the lower and upper bound of each variable of the multivariable objective function, then we generate random numbers which represents any number between the lower and the upper bound of each variable. And if we look into all the variable, it is going to give me a vector representing the location within a search space. If we are developing those locations, then we'll get many such locations depending on our desire. In this particular method, we should be generating as large number of locations as possible to ensure that the search space is appropriately covered. This particular method to ensure the number generation can be seen in this step 2 of the algorithm. And once we do this, we need to evaluate the objective function value at each of these locations. And after evaluating, we need to find out the optimum value of the objective function and report the corresponding location as the optimum location for this problem. Now the method looks very simple. We have to just populate the search space with various random location and identify the optimum solution. However, there are certain disadvantages. The primary disadvantages in this method is that since we are not using or utilizing the objective function value of a single location to understand the relation of that objective function value with respect to the neighborhood, which means we are not sure whether that particular solution has already reached optimum or not without evaluating all the location. So in this process, basically we end up evaluating very high number of objective function in order to find the optimum solution. Now you can imagine if the random point which you are generating, if it is not well distributed, then there is a probability that we might miss the optimum solution. Sometime in this method, the best obtained solution may not be even close to the optimum solution of the given problem. So these are the general drawbacks. However, this method can be used if we do not know where the optimum lies to identify certain points or certain location which is very close to the optimum solution by randomly searching within the space and finding out where the optimum is obtained or where the best solution is obtained. From this best solution, we can use other methods to reach the optimum solution. An improvised version of this method is a random walk method. Rather than evaluating all along the search space, we choose one particular location and then in that location for a given step size, we try to find out random direction to search, and once we search in that random direction, if we find that the new location is better, we start our search from that location to another few directions for a given step size, and the process continues. Let's look into the algorithm of this method. So in this algorithm, we are first setting the counter k equal to 1 and m equal to 1, which indicates the maximum failed trials for each step size we are considering. So definitely we need to indicate the step size for this, and we also need to know where we are going to start. Now once we know this, we also need to set up the termination criteria, and this termination criteria could be dependent on the objective function value or could be dependent on the step size. So in either case, we can say a small precision for the step size or the function value can be set at the step 1, and once we do that, for the start point we do evaluate the objective function value. Once we do that, then we go to the step 2. In this step, we find a random direction to search, and as we find the random direction, this random direction is governed by the random numbers generated. So if we have n number of variables in our objective function, then we can generate n different random numbers between -1 and 1, and if we do the square root of the square of those random numbers and that number r is less than equal to 1, then we can use it to find the direction in this way. The reason we set this r less than equal to 1 to ensure that the direction we choose is not along the diagonal of the hypercube formed around a particular point. Once we know the direction, we can easily find out a point in the neighborhood of the given point xk for a given step size s by using this particular formula, and once we find that point, we need to evaluate the function value at that particular location. Then we need to move to the next step, which is step 4. At this point, we need to compare the objective function value of the new point which we just obtained with the objective function value of the point which we had earlier or from where we started, which is xk. If we find that the new point which we obtained is better, then it is good, we need to increase the counter k equal to 1 and move to the step 2 to find a new direction for a new location. And as we go there, we need to set m is equal to 1. Now if it doesn't happen, we find that the new point is not better than the older point, but it is equal or worse than the older point. In that case, we also need to additionally check that if our counter of these failed trials had reached the maximum number m or not. If we had reached that maximum number, then we need to do something else, but if we haven't, then we need to increase that counter m by 1 and then we have to go to step 2 to find another direction to search. And by chance, if we max out the number of failed trials, then we have to go for this condition where we are saying that it has exceeded the failed trial. Then we need to check as well that our step size or whichever condition we have set for the precision, it could be function value as well, is still more than the precision we want to achieve or less. If it is more, then we need to set the m counter, the failed trial counter, back to 1 and reduce the step size. Once we reduce the step size, then we go to step 2 to find a new direction and then the process continues. If all these conditions are not satisfied, then we have reached to a point where we have obtained the required precision and hence we are terminating the process and reporting the location which is better for this particular objective function. So we had 2 points, xk and xk plus 1. We need to compare the objective function value at that particular location, and whichever is going to give us the better, we need to report that. Now in this method, as I said, it is like you have a search space which can be defined in a two-dimensional space for two variables like this, and you are starting from a point here. So you take a random step of a fixed size in some random direction, which is, say, suppose we took a step here where we found that the objective function value is better. If not, we have to take another direction. In some direction, once we find that the objective function value is better, so for this case, let us assume the objective function value was found to be better at this location. So we move from here to here. Then again from here, we look into the random direction of the same step size of this much and try to find out. And in this case, if we find that a point or location here is better, so we move to this point. Now at this point, if we start searching for the better point all around this by taking the random direction of the same step size and found that we couldn't find any better solution and we have exhausted the failed trials, then instead of the step size of this length, we are going to reduce it. So our search boundary is going to now be around this. Earlier it was like this. So once we reduce the search boundary, we try to find out if we can obtain a better solution. And if we can, we move to that location. If we cannot, and if we exhaust all our failed trial option, then we further reduce the step size and this process goes on until we reach the condition where it meets the predefined precision, and once it meets that, we terminate the process and report the point as the optimum solution. So in this method, if you see that once we found a better point, we again started randomly searching all around that point. We never cared for to see whether if we had taken one more step in that direction, whether we could get an optimum or better solution or not. So an improved algorithm for this is the random walk method with direction exploitation. So once we find out that in a certain direction we have better solution, we try to go as much as possible in that direction until no further better solution is obtained. So this process is similar to the random walk method. However, we do exploit that direction and there is no fixed step size. Rather, this step size is decided based on the direction and how much we can reach. So to understand these all three methods clearly, we have examples to look into. So in this example, first we are going to look into the random jump method, and this is our objective function, and this objective function has two variables x1 and x2. Both of these variables, the upper and the lower limit are given here. The lower limit is -2 and the upper limit is 2. Now we generated random numbers between -2 and 2 as shown here. These are all randomly generated locations. So this is one set, this is another set. It's a continuous set of numbers or the locations which we have generated, and in this many numbers, once we evaluate the objective function and compare, then we find that at this particular location the objective function value is the minimum, and at this particular location the objective function value is the maximum. So even though we are saying this is minimum and the maximum, the better way to say is these are the best solution obtained, because we exactly do not know whether any better solution can be obtained in the neighborhood of this location or somewhere else. So this uncertainty do remain in case of random search methods. Now the same problem we'll look into the random walk method. It's the same objective function, and in this case we need a start point. For that we had set up a start point as -2, -2, and when we evaluated the objective function it was 8. Then in this particular problem we had set the initial step size of 0.5, and then we evaluated a random direction which met all the condition and found out this is one of the random direction. So using this random direction and this particular step size, this point can be represented as this, and at this particular point we find out that the objective function value has improved compared to the previous point. So we can use this our base point, which we have written it here, and then for the same step size we go and look for the some random direction, and then again we see the x1 and x2 values, and then we find out the objective function value. Now there could be many iterations to obtain a right or correct direction. I have avoided those, but when you are going to solve this problem using the random walk method, you will find that in between these two steps there could be more than one steps, where in certain direction or certain cases it is almost exhausting the failed trial, or some failed trials are there. Now once we know this, in this case we found out that the objective function value improved, so we choose this point as the better point. We move to the next iteration and this process continues till we reach a point where we see that the objective function is 0.32 and our step size is 0.5 still, and beyond this point we found out no further improvement can be achieved. We need to reduce the step size and continue the process, and if we cannot further reduce the step size, or if we cannot further find any better solution even with the reduced step size, then we terminate and report this last point as the optimum solution.